now a dedicated session on treatment planning. First, we're going to have an introduction on basic principles from Joao Seco from DKFZ, because we are using the treatment planning developed by DKFZ for education and training purposes. And this is exactly the tool that we will have used in the first school, as I will say later, and also on what we call particle therapy master classes that are full-day events addressing actually high school students. So the whole session of Train the Trainer that we are going to have has a little bit the meaning of training the people here on using this tool, with the hope that these tools can be used later in the Home Institute to also contribute in this kind of events. But of course, we are mostly interested for people to use it for their own research, and Joao Seco now is going to give us the introduction to the treatment planning. Thank you, Joao.
All right, let me just try to share. Okay, I will wait patiently now until it comes.
Yes, there it is. Thank you.
Okay, so hopefully you just had a really wonderful lunch, and I will start with a small introduction on treatment planning. I want to mention that a lot of the work was also developed by my colleague, Nicholas Joao, who will give you a lot of the practicals. His postdoc will do that later on today. So let me just see if I can move this. Okay, so from a treatment planning perspective, from a radiation therapy perspective, there are literally many steps to forming a so-called plan, or sorry, effective radiation therapy treatment. There's the patient fixation, imaging, identification of delineation, treatment planning, verification, and QA. And a lot of these things have already been dealt with. I'm going to focus on the treatment planning aspect that is one of the key elements of the whole process. So let me see. Okay, so what is a treatment plan? It is something that is really going to represent the final plan that we will give to the patient, and it should fulfill at least the clinical requirements. So it's important that the treatment plan have right at the beginning what the clinician needs for us to achieve the so-called treatment of the cancer. It should also try to account for the biological processes. So in principle, you're going to give radiation to the patient, and you want this to effectively deal with the cancer. And above everything, you have to model many times the physical and the chemical processes in the form of reactions or interactions. Most of the treatment plannings do mostly the physics interactions, not so much chemical, but this is also coming online now in many of the new softwares. And in the form of dose calculation and an optimization, you try to build an optimal plan that in principle you would then deliver to the patient. So there are many stages. There's the clinical part, there's the biology part, there's the physics part, and there's also the computational part related to dose calculation and optimization. So it is a very complicated set of problems, and in many cases requires inverse solution, so what we call an inverse problem. So let's start with the simplest thing, imaging, right? So imaging started with X-ray, and X-ray made it possible for us to do the first types of radiation therapy. But the key development that was made possible for treatment planning has been the CT. So the CT has given us 3D images of the patient on which we can do treatment planning. And the 3D CT is acquired in the form of axial acquisition or even conical acquisition. Here's an axial acquisition where the rotating tube will go around the patient, acquiring 2 or 3 or 4 slices per time. And you see on the right an example of a CT. And what do you see when you see a CT? You build an image that looks like this. These are different slices of the brain. This is in the eye level, this is a little lower, and this is the part of the teeth, right? So you see the dental part here. So CT is also shown as bone image because you see very well bone contrast. So you see very clearly the difference between white, which is the bone tissue, and dark gray, which is the soft tissue. So CT imaging has a very strong contrast between bone and soft tissue. However, within the soft tissue, it's usually pretty hard to really distinguish components. but it offers the information that we need for the treatment planning, which is the electron density. Here's an example of looking at the patient from different directions. This is a transversal axial slide. This is a sagittal slice. And this is a frontal or coronal slice. These are the three definitions that are used to characterize. So axial, sagittal, coronal. Then one part of the treatment planning process is also the delineation of the organs, right? The volumes of interest have to be outlined by the clinician. So this is the responsibility of the clinician. And he has to identify the outer region, so the head contour. He has to define all the critical organs plus the tumor. So if you can see right in the middle here, the pink region is your tumor. And here you have sensitive organs, which are the brainstem, the chiasm, which sits over here, and the optic nerve, this little leg, and this leg over there. And then you have your eyes also. So the most critical organs in this region is the little butterfly here, which is your chiasm, and the brainstem in green. These are the most sensitive organs that sit right next to the tumor, which is this pink. So the ideal dose distribution, I'm going to represent the ideal dose distribution for a situation where you have a tumor in green and a surrounding organ in a red. Okay, so ideal dose distribution would be such that the tumor is in red and the organ is in green. The ideal dose distribution would be the dose that you deliver all the dose to the tumor, which is the red, and you spare the organ that's sitting in this U-shaped geometry. Right? This would be 100% to the red and 0% to the green. This, of course, in practice is not possible, but I will show you now the different types of estimations that we can achieve. All right, so how do we do treatment planning? The first treatment planning that started over 50 years ago or even longer is called 3D conformal. And 3D conformal basically involves delivering a photon beam to a specific tumor at a certain depth, and using some form of collimation system, either an MLC or a collimate or an aperture, and you shape the tumor that you want to deliver in a beam's eye view. So you look down the beam and you see the tumor, and you shape the collimation system to the tumor. And adaptation of the photon beam is done to the tumor shape and in the direction of the beam, looking down the beam, right, which is called the beam's eye view. In the case of a beam's eye view, you see it here in yellow. You have the beam coming in. You have your depth dose, where the maximum dose is close to the skin. And you see that it's very hard just with one beam to achieve a very good coverage of the pink. So you see the dose basically does not achieve a uniform dose with one beam of this tumor. And definitely you're going to give very high dose to the yellow, which is your organ. So what you need to do is you need to add multiple beams. So if you add multiple beams, as I'm adding here, left to right, clockwise, you'll see that eventually I will get a really good conformality of the tumor. But I'm also giving a very high dose to the yellow, which is the organ. Right? So this is called 3D conformal, where I basically adapt the dose to the tumor along the beam's eye view. But the problem is that although I can achieve a very high dose conformality to the tumor, I cannot spare the organs that are situated inside a small concavity. Like this is a U-shaped concavity, which is really hard to spare organs in this cavity. So in this case, I give high conformality to the tumor, but in principle, I would also get high toxicity to the organ that's in yellow. So this is really a not acceptable situation. Okay. So can we do better? Can we do better? Yes. And this is what we're going to discuss in the next steps. So to do that, we have to introduce the concept of beamlet. So instead of delivering a broad beam, which is what we were doing before, we are now going to deliver pencil beams or beamlets, right? And they are going to be relatively small, allowing us to cover the whole tumor with small beamlets. So here is, for example, one beamlet on the edge, a second beamlet, a third beamlet, a fourth, and a fifth. So with these 5 beamlets, I was able to cover the whole tumor from top to bottom, right? So how do we calculate these beamlets? Well, there are different algorithms to calculate the depth dose. Notice the dose is hot again at the surface and cold as you move deeper. You can do either analytic pencil beam calculations, which are extremely fast. These are usually pre-computed based on measured dose, right? And they're usually done in water. So these pre-computed algorithms are based on water calculations, right? They are deterministics, they are extremely fast, but they have problems in dealing with heterogeneity. So with changes in the density, tissue density. An alternative is to use Monte Carlo to calculate these beamlets. And under these conditions, you can really accurately model all the changes in densities and depth. The only problem is that Monte Carlo dose calculations take a very, very long time. So usually algorithms that do calculations of beamlets start with a first pre-calculation in the form of an analytic, and then further on they do a 1 or 2 dose calculations with Monte Carlo. So we'll show how that works. So here's, for example, intensely modulated with pencil beams. Intensely modulated is you're going to have, for example, 5 beamlets, and each beamlet will have a slightly different weight. So here are the weights, the W, and each beamlet will have a slightly different weight such that you can spare the organ. So in this case, you see that with the 5 beamlets, I can deliver the most of the dose to the edge of the tumor. So here's the upper part and the lower part where I give more dose. And through the middle, I give less dose. So I can control the intensity of each beamlet by using a weight W. And like this, I can control for every angle where the high dose goes and where the low dose. In reality, in a treatment plan with many beams, you have a lot of beamlets per field. And in total, you will have between 5 to 12 fields. So you have in the order of 10,000 beamlets or more. So let's go back again to the ideal dose distribution. This is the ideal dose distribution where the red is covered with the radiation and the green has nothing. What we need to do is now to develop a mathematical way of trying to achieve that dose distribution. So we have to define a dose vector, D, and then we have to convert the information from the fluence matrix to the dose. So what we call the Dij matrix, where this D represents the conversion from a beamlet information in fluence space into the dose information. So I'm just going to draw now just so that it's possible to see. So this is my dose information that enters into the beam, this part of the circle, and my fluence information is the information that is just above the entrance. So this is represented by a pixel. So I have a certain intensity, let's say my W that I mentioned before. And this is my fluence space up here before it enters into the beam. And this is my dose space when I do calculations in the beam, in the patient. In this case, it's really important to have the two. And what you do is you convert one to the other with the help of so-called Dij matrix. This is the D matrix here. Just close that again. So then everything is controlled by the weight, right? So you'll have a weight that tells you how much each pencil will convert fluence to dose. And this allows you then to control the dose that you give to each region in each beamlet. Okay? So here we have ultimately the final matrix. The dose in the medium is regulated by a W, which is the fluence space information. So I want to just make that clear again. This is in dose space, and this is in fluence space. So dose space is inside the patient. So I'll put a capital D here to represent the patient space, and fluence space is everything outside the patient, which is coming in from the beam, right? So you could have a beam with 1 pixel here, for example, or you can have another pixel there, right? These represents 2 intensities, 2 Ws, represent fluence that's been delivered, and the dose space is the dose that then corresponds to that pencil. Here's an example of 2 dose points where you see 2 horns, but you can have much more to represent the whole thing, right? So the dose space is inside the patient, the fluence space is outside the patient and corresponds to the beam information. Okay, so how do we find the correct vector? Well, the D equals dW has no exact solution, so we have to add a small epsilon, and we try to approximate D star, which is the optimal solution, by minimizing the epsilon. So there are different ways to do that, but the simplest way is to produce a quadratic function in which we're going to minimize. So in the case of a quadratic function, which is represented here, again, I will put it right. Notice that there is a quadratic function here, dxt. Sorry. There's a quadratic xt times a p and x. This is effectively what's represented here. And this represents a quadratic function that means that you have a minimum. So when you start your optimization at a specific point, it eventually converges to a minimum, and your minimum would be some point in the valley here, right? And that you can guarantee that the minimum exists because you have a quadratic function. There will be a minimum to which it converges, right? We will see this in a 2D representation in the next slide, but I just wanted to make it sure that it's clear. So you're going to minimize this dW minus d star squared, right? So how do you do that? Well, imagine that my parameter space looks like this, right? I have my minimum of my space here at this dot, and my starting point starts somewhere here, W. So this is my starting point of my optimization. This is my bidimensional space with two weights, right? A W1 and a W2. When I do optimization using this method, I basically start with a W1. I have an objection function that calculates the position, and it calculates the gradient. So the first step is always the gradient and then the direction. So like this, you take one step closer to the minimum, and then the next step moves it on to the next one and the next one, and eventually you converge to the minimum point, right? And in short, this is a quadratic surface with a minimum. So I can even draw the quadratic surface somewhere here, and there's the minimum there, okay? However, you also have to guarantee, and I want to just to point this, sorry. I apologize for this shift. You also have to guarantee that your weights are positive. You cannot deliver a negative weight of radiation. So in the previous solution, the first step was going into a negative weight. Notice that is in the negative domain of W1. So you have to guarantee that both weights are positive, because you are delivering positive amounts of radiation. A negative amount of radiation would be to remove the radiation, which you cannot do, right? So you also have to be sure that you always have positive solutions. That's why you need to solve this in an iterative form. Okay, so here's, for example, your 3D conformal that we started with before. And let me just overlap now the IMRT. The IMRT allows you to then remove the dose from inside the organ at risk. So notice that previously this was fully covered with maximum dose, and now this is significantly lower dose. So this is probably at around 20% of the previous value. So it's much, much lower. And this you do by controlling the intensity of each direction. Notice there is a hole here, and each beam has a little hole, which means the weight of this beamlet is much lower than the weight of the ones neighboring it. So you see here, there's again a cold beamlet, a cold beamlet, a cold beamlet. In this case, it was intuitively straightforward to observe that you're going to get a cold beamlet along the distribution of your beamlet, along the beam. Okay, so that was to give you an overview of how intensity modulated works. Now we're going to move into heavy ions and hadrons. Okay, so the old way of delivering radiation with particle beams, right, is something called a passive scattering system. The passive scattering system has multiple stages. It's got a first scattering step where it broadens the initial pencil beam that's coming in from the machine, either the cyclotron or the secantron. So this initial step is to broaden the initial pencil beam. Then you have your range modulator, which is going to change the energy of the pencil beam. So you have different thicknesses of the range modulator wheel, okay, or ridge filter. And with the different energies, then you have the correct depth eventually of your treatment. Then you have to go through a second point of where you have a second scattering system that broadens the beam from the pencil beam shape to a broad beam. So here you have a very narrow pencil beam, so it looks something like a Gaussian, almost like this. Right? And here at the end, you would have a broad beam, so almost something like that. Right? And to go from the pencil beam to the broad beam, you need this scattering system which broadens it here. Okay. Okay, so then with the scattering system, you broaden the beam, and finally you have the compensator, which will model directly the shape of the tumor. So notice that this shape here is literally the inverse of this shape at the distal edge, right? So I want to just point out that the old style approach, the range compensator, this shape is literally modeling this shape here. Okay. And you see it is literally the inverse of that. So this range compensator models that, and you see a repetition of that same geometry at the entrance part. So you have basically a copy at the deeper part, which is what you're modeling, and at the entrance part. And this is a disadvantage of the passive scattering system, because you'll have a hot area here where there's no cancer, you'll have a hot area here, and you can also have potentially a hot area here. So you see these three hot areas appear as a consequence to the fact that you're only modeling a specific region. What about IMPT? So IMPT is an alternative fashion where you can use pencil beam, and I think so. The pencil beam approach allows you to improve your delivery, and we don't need no more the collimator, right? So the pencil beam allows you to deliver pencil beams of protons you have much better control, you have much better dose distribution, and it's very easy to simulate with both deterministics and Monte Carlo codes. Because you also have the much higher number of beamlets, you can control the modulation of the dose in depth. So you can control the modulation in the deeper part, but you can also control it in the shallow part. So here's, for example, an example. We have a tumor. You see that there's a pencil beam coming in from the right. And if I give another pencil to that one, I can basically create 2 points. I can have one pencil delivered dose here, and I can have another pencil delivered dose there. And like this, I can keep going all the distribution and deliver any shape and dose distribution. Okay. So I just need to cover this whole volume with multiple points. So here again, you see the pencil beam moving across, and with the pencil beam, I can achieve any depth, any distribution, and even reduce the dose to the critical organ here. So notice that the dose is not much lower than before. It's very, very close to 0, while before I was in the order of 20% of the total dose. So this is a very powerful way of allowing us to control very accurately the dose given to the tumor with pencil beams. It does require that you have an optimizer that can find the optimal weights to deliver a 3D dose distribution from multiple beams. So remember that I had a matrix, a dose influence matrix that connected the fluent space to the dose space. Now you have to now calculate one for protons, which is different from the photon, but it uses the same mathematical formalism. Right? In the case of proton pencil beams, what you do is you have multiple points in which you're going to calculate in the tumor, and here you have all the points, and there you have all the pencil beam lines. So for example, the red region, which is the tumor, is covered by 5, 6, 7, 8, 9, 10, 14 pencils, which are the points that represent the dose given to the whole volume needed to cover the tumor. So what happens if you do this for the same example phantom, and now I slowly build up the dose so that you can see it. So pay attention to the figure on the left, where you have the dose distribution just of 2 pencils coming in at the moment, and the dose volume histogram on the right. I will explain a little better the dose volume histograms later, but you'll notice that this will converge towards a step function, and on the left, the tumor dose will converge to a homogeneous dose as I add pencil beams. So I'm adding pencil beams all over the tumor volume, and I'm slowly converting it to a more homogeneous. So now you see a very homogeneous delivery just with one beam. I did not need many beams like photons. With one beams and intensity modulated proton therapy, I can achieve a relatively homogeneous distribution while sparing the organ. And notice the step function. This step function means that I have a full homogeneous coverage of my tumor. So let's have a look at the liver cases where we compare photons, protons, and carbon. So here's an example of a carbon beam only. The physical dose, again, the physical dose is just if I just focus on the bright peak delivery of the dose, it's homogeneous. But if I focus now on the biological dose for carbon, I have to change the physical dose to achieve a biologically equivalent dose. So the same physical dose in carbon induces completely different biological effect in carbon beams, right? So clinically, carbon beams have an RBE of 2.2 to 2.4 for most patient cases. So we always have to take into account that this changes also with the LET of the point in which the dose is delivered. So now if you look at the physical dose of a carbon beam, you see the physical dose looks very odd, but the biological dose is what we plan on for the tumors, and you see the biological dose is the one that is uniform, okay? Now, the physical dose to biological conversion is just a matter of correcting based on RBE, right? So you have an RBE correction of the order of 2.2 to 2.4, which is LET dependent. So the RBE needs to be accounted when we do carbon beam therapy. It's commonly not accounted for when we do proton therapy. So that's why it's not so straightforward to see the difference. Now, let's have a look at what happens when we do the same liver case for all 3 types. The photon case requires always many beam directions, right? You can always with IMRT achieve relatively good conformality to the tumor, but you see this dose creeping into the organ. It's usually a little higher. but you also see a lot of background dose. So you notice that the whole body has relatively blue colors. That means the patient is getting a significant amount of background dose. In the case of the protons, I can do the whole delivery with 1 or 2 beams, right? It's common not to use only 1 beam. Clinically, we use usually for protons 2 or 3 beams, but it has the example of 1 beam that achieves a really good coverage, right? And for the carbon, you have the same type of effect, but you have the exit dose from the fragments that you produce with the carbon. Okay, so how do we do the analysis and quantify this? Well, there are many ways to analyze this. We have usually 2D tomographic images. This is a 2D tomographic image where we look at isodoses. We can also do dose statistics by looking at the mean, the maximum, and the mean dose. And we use also dose volume histograms. That's a very unique thing that was developed in the 1970s by Michael Goiting at MGH. And we can also use biological models like TCP and TCP that give us a better biological estimate. So here's the dose volume histogram that I mentioned previously. The dose volume histogram represents the volume irradiated on the y-axis as a function of the dose given to the volume. Usually it's not given in relative dose, it's usually given in absolute dose in gray, but here's an example just as form as a relative dose. So I usually say that 95% of my tumor is getting a dose D. This is what this is representing. So the point here where the arrow is, it says 90, close to 95, probably 93% of the volume is getting a dose D or higher. Okay, so this is the dose or higher. So if I'm down here at 100%, that means 50% of the volume is getting 100% of the dose. Okay. What about the biological models? The biological models usually translate into what is called sigmoidal curves, right? Where the probability of control, tumor control, or the probability of toxicity increases from 0 to 1. Okay, so this is a probability 0 to 1 or 0 to 100%, whichever you do. And on the x-axis, you just have dose. That means as I increase the dose to my tumor volume, the probability of control increases. So let's say I give 50 gray, in this case, 50 gray corresponds to 50% tumor control. But if I give 80 gray, I have close to 100% tumor control. Right? But the difference is that 50 gray, I have basically no toxicity, only 20% toxicity. But if I do 80 gray, I have a significant amount of toxicity. So although I get 100% control of the tumor, my toxicity is so severe that very likely the patient would not survive. So the key is to find a solution that complements the two of them. So somewhere here in the middle of this two, you have a maximum effect. So around, let's say 60 gray, probably 60, 70 gray is the optimal effect where you have this maximum. So there are a variety of models for predicting these TCP and TCP curves. You have the Lyman-Kuchar-Burdner model, AKB models. You have also recently more machine learning and AI-driven models. And you have a variety of other ways of doing it, okay? Most of the most recent treatment planning algorithms now use some form of LKB or EUD model for modeling the biological effects. So how do the more complex prescriptions work, okay? So this is the way we have to implement the mathematics, but we have to understand what mathematics translates, right? So for example, let's assume that I want to achieve a mean dose of the parotid gland. Well, that's one case. The doctor said, I want a mean dose of a certain value. Or what happens if I want to achieve a coverage of 60 gray of the tumor? Or what about it not exceeding 110 gray? So these are 3 examples of possible requests from the clinician, right? So let's have to see how they translate to mathematics, right? So let's start with keep the mean dose of the gland low. So here is my mean dose, right? I want to minimize this value of my mean dose, right? Keep the mean dose of the gland low. So minimizing the mean dose, right? An alternative is to achieve coverage with 60 gray. So a 60 gray coverage means I want to minimize this quadratic function with where the D value here is 60 gray, right? So the D hat, right, would be 60 gray, and you minimize this quadratic function, and that will push you to a mean to achieve 60 gray coverage. What about the option of not exceeding 10 gray? So the dose cannot be higher than 10 gray into the brainstem. In that case, you use a cost function that looks something like this. You have D max D log, and you have a function here that forces the dose to be below that maximum dose. Right? So these are different examples of how you convert a request from the clinician in light blue into a mathematical function. What about optimizers? You have different types of optimization process. You have the interior point method. You have the sequential quadratic programming, which is what is used now, for example, in RayStation. So here is, for example, a set of constraints that the clinician can say, right? So if you see these little pink crosses, the clinician says that the max dose to the brain stem cannot reach 1 gray, for example, or that the dose to 40% of the volume cannot be higher than 0.5 gray. So the dark green is the cerebellum, and the light blue is the right parotid gland. So these are things that the clinicians will draw. You will identify on the DVH that these are the constraints that the plan has to sustain, right? And so you build an optimizer to be sure that you get below these points. So these are examples of those constraints on the cerebellum, also in the brainstem, which is this early green one, light green. And that's the maximum dose constraint. So this is a maximum dose constraints. These are partial volume constraints. When you use optimization, you tend to use nonlinear constraint optimization, and you implement a set of objectives, usually in the form of a quadratic objective, right? So here you have a square deviation where you calculate that, and you have the constraints, right? So the objectives is what you want to minimize or maximize, and the constraints are within which this domain is working. So let me just draw a phase space, right? So imagine I have a function here. I set an objective with functions like this. This would be my objective. I want to find a minimum, and I set my objective using one of those functions, okay? But now I also have constraints, and constraints are basically block. I cannot be below this region. So the dose has to be around certain Dmax above it. Or I could have another constraint up here. Let's say the dose cannot be in that region because it's too hot for a certain organ. So the optimizer has to start in this region somewhere. Let's say it starts here, the first step, step 1, 0. And then it has to travel to another point there, and then another. And if it travels beyond the constraint window, let's say it travels here, the algorithm has to be able to stop it at the interface of your constraint, and then to continue from there onwards to the point that you needed there, for example, right? So this is important, that the constraint optimization must be able to do that. So when it's constraint optimization, you have all these constraints that you add in, and you need to have the optimizer to be able to find these points and reach these constraints and travel from these constraints, okay? If you have an unconstrained problem, it's a lot easier. You don't have to worry about these constraints in the multi-parameter space, okay? And the key point is that you have to remember that it's always a trade-off between tumor coverage and toxicity. So this is the decision of the clinician, right? So here is an example of different dose plans. You see how hot or cold the organ in the middle gets, right? It's very cold. Now it's very hot again. Now it's very cold. The decision is to the clinician at what level of dose goes to the tumor and what level of dose goes to the organs, okay? And the problem in many cases is that you have many weights. That trade-off is controlled off by weights. So I wanted to emphasize that. Imagine that you had a tumor dose, which is the weight of the tumor. I'm just going to put this in squared, and you also have the weight of the organ, which is also dose squared. So usually what happens is a physicist has to play around with these weights, and imagine that you have two organs, so O1 and O2, right? And they will be contributing to your objective function. So this is my objective function, which is quadratic, all right? I've just put them, it's T squared and O1 squared and O squared. But the problem is that you have these weights that can be any random number of weights, right? So you have to find the optimal solution, but you have to play around with these weights. And this is really a very complicated process. The only way to get it right, the only way to get it right is use multi-criteria optimization. So let me just bring back the annotate and I'll clear this. The only way to find the best trade-off for all the possible weights is what is called multi-criteria planning, right? And in this case, now you focus on the weights, right? So imagine you have T1, O1, and O2. You find the optimal solution by playing around with these weights, right? So you need a multi-criteria decision process that can find the optimal solution for all these possible weight combinations. And for that, you need to use a Pareto surface search, right? And the Pareto surface says at some point, all these weights are connected, right? And if you do the search for the optimal weight on this surface, you can then find the best solution quickly, right? So let me just translate this into a diagram, right? Imagine that I have two weights, W1 and W2. These weights seem to a certain level independent because they are two things, the target and the organ. But in reality, there's a specific point at which they are connected, beyond which you cannot change one without changing the other. So if I'm here, they are unconnected, but once I hit the surface, I cannot go beyond the surface. I can only go up and down the surface. At this point, when I hit the Pareto surface, so this surface is called the Pareto surface. It's a hyperplane. And when you hit the surface, the two weights are intimately connected. So every time you change one weight, you affect the other weight. Right? So what we do with multi-criteria optimization is we try to find this Pareto surface for all the weights present, and then you navigate along the surface to find the optimal solution. And so then you have a navigation algorithm that goes through the surface up and down until you find the optimal solution. So multi-criteria optimization is finding the best solution for all possible weights, but you do it by first finding this Pareto surface on which then you navigate. Okay. So this is the big difference now for most algorithms that exist out there. They usually do effectively that, a multi-criteria decision of the possible plans. So here's an example. I'll just repeat this video so you can see how the changing of the information in one direction is affecting the dose in other directions. This is by changing the weights of different organs, how I affected those in other regions. So this is very important because this means that once you hit the Pareto surface, you start to influence all the weights are connected. So how do we understand and solve? Well, here is another thing that we always have to account for, which is, of course, uncertainties. So in reality, when we do treatment planning, we have daily variations of the position. Usually it's random, sometimes it's systematic. And in the case of particles, we also need to take into account range uncertainty. Notice how the patient is moving every day. And you also have the problem with motion. Here's the breathing motion, and you see how the things are moving up and down. So how do we deal with uncertainties? Well, we add in what we call margins. So this is the gross tumor volume. The doctor usually draws a CTV. And to the CTV, we add in the additional margins that represent the uncertainties. Okay. How do we do for range uncertainties? Well, in the case of range uncertainties, it's very specific to the particle beams. I have an example of a tumor that I want to treat, light blue, and I have an organ at risk, which is the brainstem. And imagine that I have a perfect beam coming in. Right? This is a perfect proton beam, and I represented it here on the left. Okay, I want to cover the blue, and I've done one beam. But because I have range uncertainties in the positioning of the Bragg peak, I cannot just irradiate the blue. I have to irradiate a larger volume to account for all the variations of the range, right? And so in reality, I shoot into the organ and I create a hot area inside the organ, right? And you see that clearly here. This expansion into the brainstem will basically create toxicity in order to account for variations. What are the margins used for the range uncertainties? It usually changes from center to center, but they're usually in the order of 3.5% plus a small shift of 1 or 2 millimeters, right? So for example, if I'm treating a tumor that's 10 centimeters deep, I can have an additional margin of 5 or 6 millimeters, right? It seems very little, but in reality, in volume-wise, it is a lot. And the majority of the tumors that have the biggest ranges are the ones that are the deepest, and those are the ones that we treat most. So 90% of the tumors that we treat are 10 centimeters or deeper, so where the margins are even bigger. So So here is, for example, how we calculate for different setups. So the values are usually 2.5 times the systematic uncertainty and 0.5 times the random uncertainty, and then you have a small millimeter adding. This was developed many years ago by Marcel van Urk in the early 2000s. And what does that translate into? You have a bigger PTV margin than your normal CTV. And he has, for example, variations of just setup errors. Notice how the coverage of the tumor changes significantly because of motion. In the case of the photons, it's not so sensitive. In the case of the protons, it's extremely sensitive to these variations. So you'll notice cold areas in the tumor. The biological effect also changes, of course, and that also changes, and you have to account for this in a way. So how do we do that? We do robust optimization. This is the only way to really find the optimal solution that is robust to these variations. So the variations can be setup, motion, range uncertainties. All of these have to be accounted for in the form of a mathematical scenario, where you assume that what is sometimes called a robust plan or a worst case scenario, which is the worst case scenario option. So the worst case scenario is that you expand your tumor much larger and you treat a larger volume than your tumor. So here's, for example, a conventional delivery without any corrections. You see how variable it is. Now, if you look on the right, a uniform beam that is larger to account for range uncertainties, and notice how uniform this one on the right is. And if I have a worst case scenario, I can even make this smaller. So notice how small the hot area is now relatively uniform, and it's smaller than this worst case scenario. Sorry, than SFUD case, yeah. I'm not sure why there is writing on the window. Okay. Okay, summary to finish the lesson. Treatment planning, we try to find the best approximation to an ideal dose distribution. There are many factors in this process: the biology, the physics, the motion, all these uncertainties. The problem is always to find the optimal solution. So we have to develop a very good understanding of mathematical tools, especially inverse planning. The most common way of doing now optimization for treatment planning is using multicriteria, because when you have many components, like 3 or 4 organs, 1 or 2 tumor locations, you have to calculate a weight for each one. And to do that, you have to have a flexible way of implementing these weights. And multicriteria optimization allows you that. In iron therapy, has its advantages in many cases, of course, but it also has some problems, and the biggest problem is usually the range uncertainty. But also in the case of carbon ions, we always have to take into account also the biology, right? So the uncertainties, the biology, and of course, in particle therapy, we have to include usually a robust plan to account for these variabilities. Okay, I hope everyone is still there. I know it's just after lunch, it's always a complicated part, so I'll transfer to you, Jotana.
Are there any questions for
Nicholas? Right?
Joao?
Yes, let me share my screen. So the first question is there a color legend for the dose?
So at the moment, I think the dose was, the color legend was on the right here, where I show 60, 70 gray. Are we talking about the pictures on the left?
No, I think it's a general question.
So yeah, there was some cases, color legends, they were usually in dose, in gray or gray RBE, or in other cases, it could also be just in 100% dose was the hot red. So in every slide, I think the color legend is identified. If it's not, then you can write to me and I can help with that.
In fact, I would suggest to take a look to all these questions, and Nicholas is going also to address these topics, so I'm sure they will be answered during Nicholas' presentation, because they go a lot to the technical aspects.
Yeah.
Yeah, okay, so we're going to take these questions afterwards.
Sounds good. There are a lot of questions.
Yes, and Nicholas is going to address them anyhow.